Hello everyone, and welcome back. Today we're going to be looking at conic sections. Now, a conic section is a section on a cone, and a section is a slice. It's kind of like what you'll see in medical terminology, where you do a transverse section across the ulna or something like that. And they'll look at these slices in anatomy, and they call them sections. And here, again, the same idea is that a section is a slice that we're going to look at individually. And in a sense, that's always what section means, but we usually think of sections in the terms of class sections or something like that. But that's what we mean. And a conic section is just a slice on a cone. Of course, that doesn't do any good until you really understand what a cone is. Now, you guys, this is what you guys think of as a cone, like a highway cone sitting on the side of the road. In math, the cones go on forever, both down and up. And so we end up with two sides on the cone, a top half and a bottom half. And they're names that you'll never remember, so I'm not going to worry. Okay? And what we're going to do is we're going to do slices across this cone. And if I take a slice directly across the cone, I will cut out a piece of the cone that looks like a circle. Okay? I'm hoping that is understood. And that's the most simple thing. Now, I'm going to use a bit of a cheat that's accurate for your intuition and not entirely accurate when I take to like the extreme cases. But in any case, here I'm working with what I call a standard cone, where the radius, this is just a bunch of circles stacked up each other. Here's a circle, and then there's a smaller circle, and smaller circles, and smaller circles, and small, until I actually get back to the origin on the three-dimensional plane. Here's the x-axis, here's the y-axis, and here, extending up and down, is the z-axis. So that's what you're seeing here, right? There's an x-axis, and then there's a y-axis, and then there's a z-axis. That's three-dimensional. Axes. And of course, that one looks like less than perpendicular because we're forcing it because there's a regular plane happening here, right? And that's what's happening in this side there. And so as z goes up, the radius up, and I think of that ratio of the radius to the height above the xy plane as a slope. Okay? And so if I'm the side of the cone having a slope of 1, then a slice directly across the cone is going to have a slope of 0. And if I do that slice, I will get a circle. And so that's the first of the 4 conic sections we're going to look. Now there are 2 special slices that are totally unique, and that's the one where we go exactly across the cone, slicing directly across, totally flat. That gives me a perfect circle. And then there's another slice we can go, which is absolutely parallel to the side of the cone. It's going to go through one and a half of the cone, but it will miss the other half. And that slice will enter the cone endpoint called the vertex, and then it will slice up the sides of the cone as it comes along. That gives me a parabola. Okay? And so you get slice like slope 0 and the slope 1. You can think of slope 0 and the slope 1 conic sections is really special, and they are separating the other conic sections. That slope 0 gives me a circle, slope 1 gives me a parabola, vertex, and then 2 points that keep on going forever. Okay? And that's what we're looking at here. The official term that we're using on this slopey thing is eccentricity. And at 0, you're going to get a circle, and at slope 1, you're going to get a parabola. And then there's other slices where I come through exactly parallel, but less than directly flat, but less than parallel. And those slices are going to hit both sides of one half of the cone, and you get a stretched out circle called an ellipse, which you'll think of as an oval. As I pass slope 1 here, end up with something which is going to hit both halves of the cone. And then I'll get kind of U here and a U shape down here, 2 U shapes. And the 2 U shapes together, we're going to call a parabola. So together what we see here, slope 0, eccentricity 0, is going to give this circle. As I start getting higher, larger, steeper slices, I will start getting longer and longer ovals until finally the oval breaks at slope 1 and I get a parabola. Just for that tiny little instant of time when I'm moving up slope 1, I get a parabola. And then as soon as I increase my slope even a little bit beyond that, it will hit both halves of the cone, giving the hyperbolas. So that's a nice way to organize these by their eccentricity. With an eccentricity of 0, we get a circle. With an eccentricity of 1, we get a parabola. Now for just exactly one eccentricity that's going to give us that. 0 for circles, 1 for parabolas. Now if I'm between 0 and 1 on the slope or eccentricity of my slice, I'm going to get that stretched out circle. And finally, I get these to get longer and longer and longer and skinnier. Finally, it breaks, and you get a parabola. And then, just at that one tiny instant, you get a parabola. And then the next instant, you're getting a hyperbola. And it's going to correspond to eccentricities from 1 up to infinity. All eccentricities are positive. They start at 0 for circles. They can go up to infinity. That's kind of like, and if you think of it like that, it's like a perfectly vertical line for the hyperbola like that. Anyway, at 0 it's a circle, at 1 it's a parabola, between 0 and 1 it's an ellipse, and between 1 and infinity it's hyperbola. Today, I mostly want to look at parabolas, because parabolas have a special form we're going to look at. It's in all of these cases, the eccentricity can actually be measured as 2 numbers, and this is the formula that you want to remember. E equals C over A, okay? So that's the one that you have to remember. And for most of the cases we're working with, that will represent the focal length, the distance from the center to the focus, divided by the semi-major axis length. That's the distance from the center to the vertex, or to one of the 2 vertices, I could say. Okay? So the circle only has 1 vertex. Has 1 vertex right here in the center. That's a vertex. I'm sorry, that's not a vertex, that's a focus. Has focus. But if I split that up into 2 foci, that will be into having an ellipse. And if I increase the eccentricity on the ellipse, passes from less than 1 to greater than 1, it will whoop. It will pierce its fundamental box and pop out into a parabola. Okay, so let's look right now at these 4 sections again. If you get a conic section, directly straight flat. Okay? Think of that as slope of on the slice. In that case, the slice on my cone will give me a circle. Okay. Now, if I increase the slope of the slice, so the slope is more than 1, more than 0, but less than 1, that's when I get an ellipse. Which you probably think of as an oval. Okay? As I continue to increase the slope, I will eventually get a slice that comes through with the same slope as the side of the cone, which I'm calling 1. And at that point, the eccentricity is 1, and you're up with parabola. All of these can be done in terms of a directrix, but in practice, we only work with the directrix for parabolas. Okay? And so, as that's the case, we want a Directrix Form equation of a parabola. And that's going to go along with the other standard forms that you're used to seeing. The standard form, factor form. There's also Vertex Form, the Vertex Form. Right? But that has to do with just moving the other two around. That vertex is just a transformation on the standard form. As the slope increases, gets bigger than 1, slice, bigger than the slope of the side of the cone. At the point where kind of the slice gets both halves, and we get both halves, that's when you end up with a hyperbola. 2 points that you're seeing here, both the vertices. Okay. There's going to be a focus somewhere in here too. 1 on each side. So that you see it opening out, as you're sitting up, we're going to be able to look at the sum. There's fundamental box with this. This is the fundamental box. Look at that on our lecture on Wednesday as we look through these. And that fundamental box is there for both C's and the hyperbolas. But today is just general conic sections and parabolas. Okay, and I'll do a little introduction on the conic sections as much time as I've got to get at the end. But we're going as much as we can, just example after example on the ellipses and the hyperbolas when we get back Wednesday. All right? So, let's get to it. These are Directrix forms for a parabola. Okay? Audio is choppy. Audio is choppy. Audio is choppy. Okay. I'm going to keep on talking for a little bit until people tell me that the audio has stopped chopping. And I'm just going to fill up the time till that has cleared up. And when people tell me that the audio isn't chopping anymore, okay, and I was getting 9:43, that was about a minute ago it started being choppy, I hope. And yeah, that would be a good thing. I need to be able to see that much more quickly. It's more visual for me if I see a hand raised. If I see a hand raised, that will I'll spot faster than I'll spot things in the chat. I'm only checking the chat as I look up from my tablet. It's about 30 degrees up from the tablet to the view on my laptop where I can see the chat. Um, as soon as as the audio clears up, I'm going to continue, but I'm going to continue gathering like this until the chop is gone. I need you guys to be able to hear me at least. I know if it's chopping for you right now, it will be chopping on the YouTube video as well. I think somebody was just trying to speak. Has the audio cleared up yet? I'm just going to be talking until somebody tells me that the audio is okay again for me. Right? So if the audio is still chopping, not really, it's still chopping. Well, one of the things about extending the time we're going to be spending on this is that I can actually wait. I can wait. I can lose a little bit of time like this. It's very awkward, but you know, we'll make this happen. We'll make this work. We will make this work. The audio is better now. Okay, so let me continue where I left off. With the parabolas, we're going to have a Directrix form. Now, as I said again, guys, if the audio starts going choppy on you, put a hand up. Just put a hand up, okay? And hopefully I'll see that. There's enough students in here that I can't necessarily see everybody's hand at once. Damn. I'm not sure what I can do about that, but I think I'll get some kind of notification. I can't see everybody's hand at once. It's not big enough. What about if I go full screen on this? Can we go full screen? That will give me a better view. Let me see. And the answer is, when I go full screen, I can see everybody in the chat. That's nice. I can see the full list of attendees now. Okay, that's good. So I don't have to scroll for that. That's good. Okay, so we have 16 people here. I'm still missing like 7, but I'll figure out who that is later. We'll work with it. Okay, so here we go. Directrix form is, we're going to use Directrix form. There is a Directrix form for all of the conic sections, but we're only going to look for it for parabolas. It's the only one that works. Now, the Directrix form of the equation of a parabola looks kind of weird to you at first because you're used to seeing y equals x squared, okay? You're not used to seeing x squared equals y. And what you're looking at here, I've written these Directrix forms where I haven't done any translations. Generally, y will get replaced with y minus k, and x replaced with x minus h. That's in order to get the vertex at the new point hk. All right? But I'm giving you the simplified version, the untransformed, untranslated form of the Directrix. Okay? And it's always square equals 4a, where a is the length of the semi-major axis normally. But here it's going to be the distance from the Directrix to the vertex. Okay? And x squared is 4ay is going to be your form. So you look at this one. This looks like y equals x squared. But we write it this way because that's the way it comes out naturally. And when you're reading the vertex form, you're going to see a square, and then you're going to ask yourself, is this thing opening up or down or left or right? Because your normal parabola is the y equals x squared, you get happy and sad, right? Either opening up or opening down. And here, we're going to have these things opening up, down, left, and right. I mean, in general, you could have it opening in any direction, right? But we're only going to look at directly, parallel to the x-axis or the y-axis, okay? So on these, you want to figure out when you're seeing a form, whether it's opening up or down or left or right. And here is the answer, okay? You see this first form. This one right here. That's where we start, okay? Now, guys, is y have a positive in front of it, or does y have a negative in front of it? 1 for positive, 2 for negative. Here, is y positive or negative? 1 is positive, plus is fine for positive as well. 1 for positive. Okay, so we got answers. That's good. Everybody sees that. Positive y. What does that make you think? Maybe the up direction? And if you think about what? If I saw y equals x squared, I would know this is a happy parabola, right? So that's where you start, okay? And always, the direction in the y, it's opening in the y direction or the x direction is going to come from what you see to the first power on the other side here. X squared equals 4ay. This is going up or down, and it's positive, so it's going the up direction. Positive y direction, okay? Now, the next one that I'm going to look at here is the next one down. See, negative y. X squared equals negative y. Y is up or down. Negative is negative up or down, guys. Is negative up or down? Down, exactly. So you see x squared, negative 4ay, down, negative y, and you read this as something that's opening down. And if you think about this one, this is kind of like y equals negative x squared, right? Just kind of bring all this stuff to the other side, and you'll see y equals negative x squared, and that's a sad parabola. A sad parabola, right? Okay. Now the other two forms we're going to look at, just reverse it, right? Now you're used to seeing y equals x squared, but we can also get x equals y squared. But we write that as y squared equals 4ax for reasons, okay? Now, this one is heading in the positive x direction. Positive x direction is right or left, guys? Right, yes. And so this is going to be right. This one is going to open right. Yeah? Now, negative x direction. What's the negative x direction? There you go. See how easy that is? If you know what to look for and how to look for it, okay? So that's what we're seeing here. The four forms, we do pay attention. It's always 4a times something. And the something that you're multiplying by 4a in this form determines whether you're going to be going opening up or opening down. Opens up if you see positive y. Opens down if you see negative y. It opens right if you see positive x. It opens left if you see positive negative x. And that's how that works, okay? Let's take a look at a couple of examples on that. Okay, let's look at this example, guys. I transformed this just by moving the vertex 3 units to the right. Instead of x, I'm looking at x minus 3. Does this open up, down, left, right, guys? Somebody tell me. This opens up, down, left, right. Okay, hands up if you can hear me. And yeah, okay, so Winter heard me because she was able to answer it. Okay, so yeah, I just needed to check that because I wasn't getting an answer to my question. Thanks, guys. You can lower your hands. I can see that I'm being heard. Okay, and so you see the x squared, guys? You see the x squared? Don't pay attention to this. X squared equals positive y. X squared is positive y, so this opens up. Okay, so let's do another example. Okay, so here's another one. And this time I've done a full transformation. I've turned, instead of the vertex at 0, 0, where I would normally have it, right there at the origin, this time my vertex is at 5, negative 2. I've moved my vertex to 5, negative 2. But that's not what I'm asking you. What I'm asking you on this question, on this example, is does this one open up, down, left, right? Okay, and again, what you're going to look for is square equals linear, and that's the form that you see. Square equals linear. Ignore this stuff and tell me whether this one opens in the positive x, positive y, negative x, negative y direction. Up, down, left, right, guys. Everybody tell me. Up, down, left, right. Thank you, Jada and Danny and Vicky, Winter and Alex and Sim. Sim says it's left. Everybody says it's left. Winter, we need to turn that to right. We're turn that around. It's the negative x direction. Okay. Thank you, Marcos and Midash and Shir. There we go. Awesome. So people see this. This is awesome. Great. Thank you so much. This one opens in. This one opens left, the negative x direction. And that's what you abstract out of it. Negative x. Ignore everything else. This value is called 4a. This value is, we will see, is 4a. This is 4a, okay? So 4a is 3, a must be 3/4. And that's the distance both from the vertex to the focus and the distance from the vertex to the directrix. And now I'm going to show you what that looks like. Here is Directrix Form. The Directrix Form. This was awkwardly done. Let me fix that. That's a y-axis there. It's supposed to be. There we go. There's my y-axis. There we go. And here's my x-axis. Clearly written. There we go. So here's a parabola, guys, and this parabola opens left, right, up, down. What do you see? This parabola is open left, right, up, or down. Right, yeah? So you know this one's going to be, according to the theory that I just showed you, this is going to be the form y squared equals 4ax. Okay? So you know it's going to be y squared equals 4ax. But now I'm going to give you the actual theory behind this. In fact, I told you that the eccentricity is the distance from the center to the focus, the focal distance, divided by the distance from the center to the vertex, which is the semi-major axis length. But in fact, if you're looking at any of the Directrix forms on any of the conic sections, the distance is actually the distance from the focus to a point on the curve. Now here, the point on the curve, P, is generic point, xy. Okay? That's a variable point, xy, on the parabola. Okay? And the eccentricity is the ratio of the distance from the focus to a point on the curve divided by the distance from the directrix to the point on the curve. And the distance for the directrix, I could take this point to that point. No, we're always talking about the smallest distance. When I talk about the distance from a line to a point, I mean the perpendicular distance. How can I get there fastest? I go perpendicular from the line to the point. Okay? So, what I want here is the distance, erase, I want the distance from the focal point to the point P on the curve to be equal to the distance from the point to the directrix. Okay? And so we're going to use our mad math skills to figure that out, assuming the distance from the vertex, to the focus is equal to the distance from the vertex to the directrix. Okay, Vicky. Yeah, go ahead and start that. And remember, guys, all this stuff will be placed up on YouTube about an hour after the lecture, so you can check it from there. And not a lot of students are using it, but the students that have been using it, you know, there it is. Mostly it looks to me like, looking at the activity, looks like students are just missing some particular spot from the video, and they use the YouTube to get back to it. Okay, so let's do these distances. How about that? So here, what we want is we want the distance from the focal point to a point on the curve on the parabola to be equal to the distance from the point on the curve to the directrix. And the directrix is a line, okay? And so for that, we need some coordinates to work with, right? So here we go. This point on the curve here is going to have the coordinates, well, how far are we? We're x is a and y is 0, yeah? Okay, and its closest point here is at, what, like negative a, right? Here's at negative a is 0. And that tells me what the coordinates of this point are. The x coordinate is negative a, and the y coordinate is just, well, I don't know, it's y. Okay? Now, given that, we can start calculating the distance from F to P. And here's the thing, guys. I'm not actually going to calculate, well, I will, but if I do the distances, I'm going to have to do square roots. And so one of the cheats that people do in math all the time is, instead of looking at the distance, we'll look at the distance squared. And that way we get rid of the square root that you would normally have in solving for using the quadratic form, using the Pythagorean theorem. Okay, so let's go ahead and zoom that out just enough to be able to frame this nicely, and also give me some real estate for working. And then we'll go from here, okay? From the focal point to the point in the curve, I see the x distance is x minus a. Squared. And the y distance is y squared. And that's got to be equal to the distance from the point on the parabola, the generic variable point on the parabola, to the directrix. And the x distance here is x minus negative a. X minus negative a squared. And the y distance is, oh, there is no y distance. The y distance is 0. Okay? Because the point on the directrix closest to the point on the parabola has the same height, right? And I'm going to stop here for just a second And I'm betting people see where the 4AX is going to come from. Yeah? Do y'all see where the 4AX is going to come from? Because what are you getting here, guys? This is x squared minus 2ax plus a squared plus y squared equals x squared plus 2ax plus a squared, well, plus 0, right? Right? Let me clean this up. That needs to say plus y squared, right? And now we can start canceling. X squared cancels with x squared, a squared cancels with a squared, and there's the 4ax popping out. Y squared equals 4ax. All right? Now there's another special distance that you want to think about, okay? Yeah. And that is the line directly through the focal point and let me get myself set up here. Okay, I'm just doing a little drawing on the side that I'm not letting you see. Okay, here we go. Almost there. Almost there. There we go. Okay. So here we go. This is a picture of the parabola where I've sliced straight through the focal point F. I've sliced straight through the focal point F, right? And this segment here, this segment here, that length right there, that segment that you slice through that goes from one side of the parabola to the other, this is called the lattice rectum. Lattice rectum. Yes, try not to giggle. But in fact, it's the same word. And because rectum doesn't necessarily mean what you think it does. In any case, the lattice rectum has a length and always has the same length, okay? And you can figure it out, right? The focal point has coordinates A, yeah? The focal point has an x coordinate of A here, yes? Because that's the distance from the vertex to the focal point. Okay? And we also know that the equation of this is y squared equals 4ax, yes? Now if x is a, this point has coordinates a, and then what's the y coordinate? Let's try it out. 4a times a is y squared, and so it looks like y is going to be 2a. So I'll just take the square root of both sides. Yeah? So this coordinate is going to be 2a, and this coordinate is going to be at a negative 2a, and the length of the lattice rectum is always going to be 4a. There we go. And that's the length of the lattice rectum. It's not the lattice rectum itself. And so to represent the fact that I'm talking about a length on it, I will put the standard absolute value bars around it. So you can see this, the length of the lattice rectum is given as 4a, and that's a standard spot. And it's also a couple of really easy spots to find on the parabola given the Directrix form. Okay? Oh, okay, no, we're okay, we're okay. I've got my alarm clock on the side because it's full screen, I can't see my clock. That's that. All right, guys? So there we go. Let's see what we can do in the way of finding the Directrix on standard parabolas. And then we'll do some examples, some plotted examples. Example. Let me put the vertex at the origin, and let me put the focus. Let me put the focus 3 units up. Okay. And what I want to do is I want to find the Directrix form of the equation of the parabola and the equation of the Directrix. Okay, so to do this one, I'm going to start with some axes. And I'm going to put my vertex here at 0, 0. And then I'm going to put my focus here at 0, 3. Okay? We all good on that? Right. Okay. Oh, let me look at this and see if it's going to... Yeah. Hi, Madash. How you doing? Yeah. I'm noticing that you're look to be using a phone today. So I wanted to check with my students using phones to see if they were using the browser version or the Blackboard app. Madash, are you using the Blackboard app? Everything's good? Are you using the Blackboard app or the browser version? Browser. Have you had problems with the Blackboard app? Because I've had 2 reports. You're using the browser, I hear that. Have you tried the Blackboard app? Did you have problems? I've had 2 reports of students that had problems with the Blackboard app. That it wasn't working, it wasn't letting them in, it was chopping, they couldn't let the sound. And that's backwards from what it was when I was doing the orientation sessions. When I did the orientation sessions, everybody seemed to be okay with it was working better with the Blackboard app. But now I'm hearing that it's actually the browser is the way to go on your phone. Okay, and that's working good for you? So it's working fine in the browser, and now it's just a lag? Yeah. There's a lag in the video, I know that. I know there's a lag in the video. And I can work around that, because I can actually see what's happening in the room on my screen. And if the screen blanks out, I can see that. That's pretty neat. The real sneaky thing is when the audio chops. That's when I can't actually tell. Any case, so here we go, guys. So here is my vertex, and here is my focus. All right? And I want to point out that the parabola always opens from the direction vertex toward the focus, right? Yeah, vertex toward focus. Now, that's the direction the graph is going to open, right? And now, what is the distance? We have a letter for this. What is the distance from the vertex to the focus? We call it what? B, don't we? What do we call it? We call it C. No, we call it B. No, we call it C. What do we call it? We call it the distance from the vertex to the focus. What do we call that? I forget. B, C, D, E. What do we call that? That's right. Thank you, Witter. Yeah, that distance is called A. Yeah? And now here's a kind of cute thing, guys. If you want to find 2 more points on the graph, we use the lattice rectum. And double that distance, and double that distance. Okay, and that gives you an idea of what the graph is going to look like when you sketch it in. See that? So there's a real fast way. That's what the lattice rectum is for. It's to give you 2 more points on the parabola really quickly. Yeah. So, I mean, scaled in comparison to the focus, the focal length, yeah, these things look kind of like really fat. Not skinny parabolas, but fat parabolas, right? Okay. So, there is my focus, there's my vertex. And the way we'll do this is the directrix is going to be just as far, the directrix is going to be exactly as far away from the vertex, exactly as far away from the vertex as the focus is. So the vertex kind of sits right in between the two. So this is called the directrix line. That's the directrix line. Okay, now, in this case, we actually have the coordinates of the focus, right? Oh. I know what I had in mind, and I know what I wrote, and what I wrote was wrong. And I'm sure some students are getting really confused because of that. I certainly did intend to have just a standard focus at 0,3 here. And I've been doing this whole thing as if I was working 3,0, right? And no, I wanted to work with just a basic y equals x squared thing first. And I'm really sorry if that was confusing to anyone. Okay. So the coordinates of the focus are at 0, 3. Okay? So what is A here, guys? What is A? What's the value for A, guys? Thank you, Winner. Thank you, Danny. That's right. It's 3. Okay? And the equation here, the standard form of the equation, is given by y squared equals 4ax, right? And here, what's A? 3, right? So that gives us the equation for the parabola as 12x. A is 3, the standard form for something opening. Oh, wow. Sorry, guys. Dang. This thing's opening what direction, guys? Positive x, positive y, negative x, negative y. Which is it? Positive y. So that's what we do. When you're writing these things, guys, it's probably easiest is to start on the right-hand side, say positive y direction. And then the other side is where the square shows up, and it's the other variable. Okay, just like that. And so the equation on this one is x squared equals 12y. Just that. Okay. And yeah, I was doing things there to get your attention on, so to work with that so that you would see how things go bad when you're not looking carefully. That's cool. But remember, you need a rule that tells you how to write these things. And to write the Directrix form, I find it easiest just to ask myself, is going positive x of y, and then just fill in the other side. Okay? X squared, right? And now the line, the Directrix, right? The Directrix has constant y, yes? So this is the equation for the parabola. Now the equation for the Directrix is going to be pretty simple. It's a constant y curve, isn't it? So it's just y equals what? Negative a, yeah? And we know what y is, what a is. So the equation of the equation for the Directrix is negative 3. I'm going to put these answers here in green so it looks pretty. And easy to read when you're looking at the class notes. Okay. So, any questions on this one? I'm not sure how I'm going to answer questions in this format, but yeah, any questions on this? Does that look like it was easy? I think we should do another example, don't you? A couple more easy examples like this, and then we'll kind of go from there. What happened here? Here's one. That's page 2. Oh, I see what happened. Okay. We rearrange. This happens. Come on, give me that. Come on. Dang you. That actually accidentally put these things in order. That's not right. Come on. There we go. Up now, do I like it? Let me go to the first page. Second page. Third page. Fourth page was that example. Fifth page is going to be a new example. Okay, so this time, let's have the focus. Let's have the focus be at -12, 0. Okay, and let's vertex at -4. Yeah, it's a vertex at 0. Let's keep the vertex at the origin. Because we got time for examples today. Okay. So remember, we're always going to go from the vertex toward the focus. Okay? So let's get this in. Give myself plenty of room as I can. To 12, 5, 10, 12. I'm seeing it. Okay. In my So here we go. Here's going to be my vertex. At 0, 0. Focus. I'm going to cut these things 2 per unit. And so there's my focus now at -12, 0. Okay, what's A, guys? What's A? What's A, guys? Somebody tell me what A is. Okay, I got one answer. I got one answer. I have one answer. What's guys? You wonder, that's the right answer. Okay. What's A, guys? 2 people answered. It's the right answer. Oh, everybody says 12. Okay, so the difference here is it's positive 12. This is a distance, and all distances are positive. A is a distance, and A has to be positive. Remember the formula, right? For AX and negative 4AX. That wouldn't make sense if it was A being positive. A is a distance, and so A is 12. A is 12. Okay? So we got that much, right? Now, I've got that -12 there. That's good, okay? And so what I'm going to do now is I'm going to create my lattice rectum so I get a nice, easy way to see this. That distance is 12, and so I'm going to go up 24 on this scale. That's going to be 10, 20, 24. Directly above. And then on the other side, actually I need a little more real estate, don't I? There we go. And so, there we are. That's the other side of my lattice rectum. And so now I can sketch in my graph. There we go. Now the same way here, yeah. This also gives me a chance to sketch in the directrix, which is going to have the same kind of thing going on. And its length, distance from the vertex, is also going to be A. There's my directrix. And the parabola is actually defined as the locus of points that are the same distance from the focus as they are from the directrix. Okay, there we go. So let's find the equation for this thing. And to get the equation of this thing, we will write which way is it opening up, guys? Positive x, positive y, negative x, or negative y? Positive x, positive y. Everybody says, Winter says negative x, and Jada says negative x. I think that should be pretty obvious. Yeah, it's negative x. That's right. Thank you, Alex. That's great. Yeah, it's negative x, right? Okay. Yeah, let me do another mic check here, or speaker check. Can everyone hear me? If you can hear me, raise your hands, please. Everyone. Everyone. If you can hear me, raise your hands. Because there's always this chance I will miss one person. Caitlin, can you hear me? Thank you, Midesh. Caitlin, can you hear me? Thank you. I need to just keep them up right now. Caitlin, can you hear me? Felix, can you hear me? Jewel, can you hear me? I know Jewel can hear me. Caitlin, Felix, Sim, can you hear me? Caitlin, Felix, Sim, can you hear me? Okay, a couple things can happen, and I want to always assume I know that I don't really know. I don't really know. Sometimes students just walk away with the browser because you guys are at home right now. Yeah, and that can happen. And sometimes it can happen because, they just walk away. Okay? But yeah, go ahead and drop your hands, guys. And also it can happen because I know, things are crazy at home. Mom, there you can. Oh, now you can hear me? Okay, that's great. There you go. Okay, so yeah, you see the hands going up. I'm asking if people can hear me. Yeah. Sometimes it's because something goes wrong with the sound. Sometimes it can go wrong because things are crazy at home, and there are little brothers yelling, and mom walking around. Some of you guys, yep, yep, I know, and some of you guys are shared computers too. It's like one family computer. I've seen students with like the really neat bedroom, and it's just all theirs, and there's the machine and stuff. That's it, and it's really cool. Okay, and then I've seen the one where it's like obviously working from like a common, the family computer in like a living room. Um, Families do that sometimes. Yeah, I understand, Alex. Yeah, families do that sometimes because they want to protect young people from bad things on the internet. Okay, because you guys don't see these things, but when you're an adult, you read the newspapers, and bad things happen to young people left alone on the internet. People take advantage of them in really bad ways. And yeah, so some people like to have their family computer in the living room so nothing bad happens out in secret behind whatever. Yeah. Okay. So I can understand that. But yeah, so I'm trying to be as accommodating of difficulties, student difficulties as I can. All right, so, but I need to check every once in a while to see how many people I got. Again, remember, guys, the video will show up on YouTube about an hour later, okay? Now, as people have told me, this thing's opening the negative x direction. So as I go to write the equation, I think negative x on the right. And that means I'm going to have a y squared on the left for my equation, yeah? Okay. Now here, the vertex is at 0, 0, and that determines the translation. Generally, it's x minus h, y minus k for a vertex at hk. Here, the vertex is 0, 0, so it's just x and y. So, here we go. And again, people told me that a is what? A is, what's the value for a again, guys? I forget. What's a? That's right, and it's positive 12, guys. Positive 12. because A is a distance. It's 12, okay? So A is 12. And so the equation for the parabola is going to be given by y squared equals negative 4 times 12, negative 48x, okay? And the directrix is happening here at negative 12 as well. X, that at 12 away, I'm sorry. And the directrix, the coordinates of the point where it hits the x-axis, this is at 12, 0. Yeah. And so I can see the equation for the directrix. And for the directrix, oh, let's be neat, because we can be neat. And also because writing more quickly just means that I'm going to be unsatisfied and have to rewrite it again. In any case, so the equation for the directrix here is obviously x equals 12. Okay? So that was pretty easy, huh? Okay. Let's do one more that looks kind of weird, that moves the vertex from the origin. And then I'm going to do as many of these applied examples as I can get through. Okay. Probably just 2. One more, though. So here we go. I could do these by giving you the equation for the directrix and either the vertex or the focus. But I think I'm just going to stick with giving you vertex and focus, okay? So this time, I'm going to put the focus at 5, negative 3, and the vertex at 12, negative 3. Okay? There we go. There we go. Okay? So let's find this. So here we go, guys. Here's the point. The focus is at 5, negative 3. Okay, and now the vertex is going to be at 12, negative 3. Okay, so there's the vertex, right? So guys, I haven't done anything else, but can you tell me immediately right now, is it going to open in the up in the positive x, positive y, negative x, or negative y directions? Is it going to open in the positive x, positive y, negative x, or negative y direction? Negative x, negative y? Okay, and the answer is always go from the vertex to the focus. The direction is always going to be from the vertex to the focus, and what direction is that? That's the negative x direction. Okay, thank you, Winner. Thank you, Alex. Okay. Now, my next question is, what's A? What's A? You should be able to eyeball that. Let me get you a little closer so you can see it. What's A? Maybe closer than that. What's A? 7. A is 7. Very good. So there we go, found A is equal to 7. And what I'm going to do is I'm going to go up 14 and down 14 from the focal point to get the 2 points on the lattice rectum and use those to sketch. 2A, 2A up, 2A down. So up 14 from -3 is 11, yeah? Right? And down 14 from -3 should be -17. And those are the 2 points in the lattice rectum. And remember, as we sketch these, we start from the vertex, and it'll open this way. Okay, guys. Now, the directrix is going to be left of the vertex or right of the vertex, guys. Left of the vertex or right of the vertex. Left of the vertex or right of the. Everybody, Winter says right. Do people agree? Jada agrees. So does Alex. So does Sim. Left or right, guys? Left or right? I got 4 people. Yeah, and this is like my best students, and it's like, I'm not. And it's always Casey. Thank you, Caitlin. Yeah, because I'm always concerned that I don't want to fall into what I call the professor disease, where I think, oh, my best student answered, and so everybody understands this, right? Because that's a really typical thing to happen. You answer a question, you hear the right answer, you keep on going. Okay, yeah. So the directrix is going to be right. It's going to be the other side, right? It's going to open one direction, and the directrix is going to be behind it. And how many units behind it is it going to be, guys? How many units? How far behind the vertex is it? Danny says 7. That's right, 7. Okay? Now, if I go 7 behind the focus, behind the vertex, on the other side of the focus, what's the coordinates of the point on the directrix that's closest? I'm going to sketch in the directrix real quick. There's my directrix. What's the coordinates of this point that's closest? Okay, and people say, yeah, plus 7 on x is 19, -3. Thank you, Danny and Alex and Winter. That's awesome. That's at 19, -3. Of course, that's just one point. What's the equation of the directrix? What's the equation of the directrix, guys? What's the equation of the directrix? And remember, always ask yourself, is x staying constant or is y staying constant? X is staying constant, right? All of these are the same point, same value on x, aren't they? All these have the same value on x, right? And so the equation for the directrix is x equals 19. Yeah? And now let's find the equation for the parabola. Now we know that it opens in the what? The positive y direction, right? What direction does it open? It opens the positive y direction, right? No? Yes, no? Which direction does it open? Negative y direction? Negative x direction, right. And so you start writing the equation of the parabola. We start writing the equation of the parabola as negative x direction. So write equals negative 4ax. And then remind yourself that the other side has to be a y squared, right? So instead of this being a y equals x squared, it's an x equals negative y squared. Okay. And what's a? A is what? 7, yeah? Yes, you can have it. You can certainly do that, Winter. And to do that, I would have to do another kind of transformation on this. Okay. And it would have to do with, I would do a 2 by 2 matrix transformation to do an angle. And the matrix transformation would be cosine, sine, negative sine, cosine. That's the 2 by 2 matrix, and you multiply that by x, y, and you get a transformation that does it, and you change that on all the coordinates. So x becomes a combination of x and y becomes a combination of x and y. Cosine or negative sine cos. Anyway, so don't worry about that. Yeah, we're only going to do, directly positive and negative. And now, guys, and so this is becoming like y squared equals negative 28x. Now, where's the vertex, guys? Where's the vertex? What's the coordinates of the vertex? What's the coordinates of the vertex, guys? 12, negative 3, 12, negative 3. That's your HK, guys. There's your HK. And now what we're going to do is we're going to send x to x minus h and y to y minus k. Okay? And that means x minus, what's h here, guys? What's h? What's h? What's h? 12, right? So I'm going to replace x with x minus 12. And what's k here, guys? Negative 3. And so I'm going to send y to y minus negative 3. Got that? So you see the y over here? That y becomes y plus 3 squared equals negative 28. And you can see it coming, right? X minus 12. X minus 12. And that's how you do the transformations, guys. Yeah. You do it all as if it was at the center. It was center of the origin, if the vertex was the origin. And then you come back and you do the last translation to account for the fact that the vertex wasn't at 0, 0. Okay? So that was a kind of fun example, right? Now we're going to do some really fun examples in the time we have left. Okay, I'm going to do some eraser. And now, yeah. So how many guys see a satellite dish on your block? Like, what are the big satellite providers? I forget, like Star or something. What are the names of the two big satellite providers, satellite TV providers? One was like Dish Network, right? And then what's the other one? It was Dish, AT&T, and Comcast. Um, they do satellite. I don't think they do satellite because like this is with a satellite dish, right? Do you get a satellite dish from AT&T or Comcast now? No, I don't think so. Yeah, DirecTV. That's the other one I was thinking. Is DirecTV owned by AT&T now? Damn. These merger things are out of control. How about Dish TV? Who owns that? Do they own themselves still? Okay, so it used to be DirecTV and Dish back when I was paying attention to television. Yeah, yeah. And they were independent companies back when I was still paying attention to television. Any case, so you know how the satellite dish works, guys? You start with a parabola and you spin it. You just spin it, okay? And that gives you a paraboloid of revolution. And that's the shape of your, and that's the shape of your satellite dish. It's a parabolic satellite dish, they call it. And the benefit of a parabolic satellite dish is, by the nature of the shape of the satellite dish, every beam coming from the satellite dish hitting the parabola, all of those will be reflected directly to the focus. And that's what the idea of how the satellites work, okay? Now, if you look at your satellite dish or the one in your neighbor's house or whatever like that, you're going to see a little box up above the actual parabola of the dish itself, right? And what you find here at the focus, at that box right there, the box you put at the focus, and that right there is where you put the receiver. And this is a place where all of the signal that's coming from the satellite gets collected, where it all focuses in, so you get the entire, rather than just getting like the little bit that you get just by pointing just like a flashlight trying to catch it right there. It's just like having a big mitt, just a big, taking your arms open wide and just gathering as much signal as you can and focusing it at your receiver until you put your receiver at the focus. Okay, so now I'm going to have a satellite dish, and I'm going to set my satellite dish, and I want it to be 10 feet across. I've got my satellite dish here. I can see it's 10 feet across, and it's 4 feet deep. You write this neatly. 4 feet deep. Okay. And that's all the information I'm going to give you guys. I want my satellite to be 10 feet across, 4 feet deep, and it needs to be a parabolic reflector. Find where you want to locate the receiver, which is a fancy way of saying, or it's an applied way of asking, given just this information, can we figure out what the focus is on this thing? Okay, now, obviously this thing is going to be pointed at some direction other than straight up or straight down, right? Okay, and so what I'm going to do, just to make life easier for myself, is I'm going to assume the satellite was just straight up above. That's an easy simplification. I'm going to assume it's straight up above, okay? And the vertex is at the origin. Okay, now I have 2 more points that I can work with, right? Because I know this thing is 10 feet across, and I'm just going to kind of like toss this in here without paying a whole lot of difference right here. It's 10 feet across and 4 feet deep. And so that's 10 feet across. That's 5 and 5 and 4. 5 and 5 and 4, I hope. Yeah. 5 and 5, and 4. That looks pretty right. So here's my dish. Of course, unlike a parabola, the dish has to come to an end, right? Yeah, and so the question is where I'm going to put the receiver on this thing. That was ugly on that side. Let me clean it up. So there's a picture of what we had, right? So it's 10 feet across. And the dish is 4 feet deep. And that's the description we had, but now I've put it on an axis. Yeah? Windard, you got a question? Or is it chopping on you? Is it chopping on you? Winter, is it chopping? Guys, am I chopping? Is my audio chopping? The screen froze. Oh. 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 Oh, thank you for letting me know. The screen froze. Well, I bet that was confusing. Is it back now? I think I got that fixed. Okay, there we go. Well, okay, so I was talking about it, but here I've got a picture on the side of my satellite dish, right? So here's my satellite dish, and obviously, unlike a parabola, you can't let the satellite dish go on forever, and so it's going to be like a particular size. And the idea here is we're going to have 10 feet across and 4 feet deep. That's the idea here. Now we're going to use this information to figure out where to put that receiver. And here's the trick, guys. I know from this information what the coordinates of this point are. What's the coordinates of that point, guys? What's the x coordinate of that point? 5, 4. It's pretty obvious the way I wrote it, yeah? Yeah, that was the real thing, was just knowing to write the graph, right? So the coordinates are 5, 4, right? Now, here we go. And the idea here is I'm going to try to find what A is. Something else going on, Winter? What's going on now? No? Okay. Good? Everything's good? Okay. Yeah. Yeah. And that's a really good thing. I can see when... Oh, that was an accident. That's fine. That's fine. I think the screen didn't freeze. I think I accidentally hit the lock button on my tablet. And was able to clear that up. But that's okay, because we were able to... I was just in the sketch, and you didn't necessarily see me do that. Okay, here, guys. Now what we'll do is we're going to come up with the equation for this thing, right? So, opening in the positive x or y direction. Opening the positive x direction or the positive y direction. Because the idea is I want to find focus, right? Which means I need to find A. Yeah? Positive y direction, yes? So let's start writing this thing. This is equal to 4A y. And so this side is going to be x squared. Yeah? Okay, so there we go. And now what I know, I mean, normally I'd be looking for like plug this in because I knew what A was, right? But this time, I know what a point on the graph is. From that, I can figure out what y is. So now I know that x equals 5, y equals 4 is a solution of this equation. So that means that 25 is going to be 4 times A is 4, or 16A, right? So A is going to be 25/16 feet. That's not quite 2 feet. That's not quite 2 feet. That's where the focus is going to need to be. Okay? And that's enough. I'm going to locate the receiver 20/16 feet. (25/16) What's 25/16? Eighths are 0.0125, and so 16ths are 0.0625. And so 8 of those is 48. I don't know. What's 25/16 feet? Above the center of the dish. And that answers the question. Okay? Yeah, so that's the other side right there. Sometimes you give it physical dimensions, and that's enough for you to be able to figure it out. Okay? Now I have one more example I think we can do, and it's a funky example. This last one, this first example was for real. For real. Okay? In the sense that, yeah, satellite dishes actually are parabolic reflectors. Okay? In other words, it's a parabola that's been spun around. We call it a paraboloid of revolution. And we'll figure out things like areas and stuff like that on those when we get to Calc 2. We won't do that in Calc 1, but we'll do that in Calc 2. So here we are. Let's go ahead and do this last example here. And boy, I'm just thinking about right there when I was thinking before, oh, I'll just do this in one lecture. That'll work. Yeah. No, it was not going to work. And I'm not even really able to introduce the fundamental boxes and stuff like that I thought I'd do at the end of the lecture today. Partly that's because I've had to wait for connection to fix itself. Okay, this is a funky, not real example. We're going to assume we have a parabolic suspension bridge. That's just not how it works. An actual suspension bridge does not follow the shape of a parabola. Yeah. There's another shape on it. It's called a catenary. That's the natural shape for a line, for a wire hanging between 2 points. The natural shape is not a parabola. It's called a catenary. C-A-T-E-N-A-R-Y. Okay, and we will look at those if we have time when I talk about parametric equations in, do I do it Calc 1? I don't know. It's somewhere in calculus. We talk about parametric equations. Okay, so, but now we're going to assume that we have a parabolic suspension bridge, okay? And this parabolic suspension bridge is going to have a girder on one side, and a girder on the other side. Okay. And the bridge on the side, this is going to have a little left right there. And now we're going to have a wire that comes from the top to the middle of the bridge. And so here's the actual parabola. And no, it's not actually, the shape is not actually a parabola, it's a catenary. But, you know, for purposes of demonstration, we'll work with it. Okay. And once again, you can see this thing happening in the positive x direction. And the information I have is that it's the the height at the top here is 80 feet. And the length of the bridge, it's 600 feet across. And now the question here is, I want to know how, and it goes all the way down to the roadway. It actually meets the roadway at the center. And now the question is, I want to know how far that cable is above the roadway, 100 feet from the center. (150 feet). From the center. Okay? So this is, in a sense, it's just the same problem we just did. But now we're calling it a suspension bridge. And making it like lots of big feet, not like these small things. A satellite dish 10 feet across is pretty big, isn't it? Because the ones you actually get on your rooftops, this is like just a 3 or 4 feet, right? You know. Any case, so here we are. And so I want to find out what this height is. 100 feet, 50 feet from the center. And I think you probably can guess what we're going to do, right? I'm going to find the coordinates of this point, use that and what I know about the Directrix form to find the equation of this parabola. Okay? And once I have the equation of the parabola, then I'll be able to plug in a different value, right? I'll plug in the correct value for x, and that'll give me the height y. Okay, so this is going to have coordinates here, and this is going to have coordinates here. And the y coordinate at the height, 150 feet from the center, is going to be the correct one, okay? Now again, this one opens up in the what? Positive x direction, right? No, it's the negative x direction. That right there, that's not parabolic. Winner, that's not parabolic. Those are ellipsoids. And what you're not seeing is that you could have done that as an oval. It's a big oval of revolution called an ellipsoid of revolution, and that particular one is called a spheroid, not a spheroid. Yeah, that right there would be an oblate spheroid. And what you're doing is you're standing in the focuses of an ellipse. And that's how you create a whisper chamber. And we'll talk about that on Wednesday. Yeah. Oh, by the way, where is that? Which science museum did you see that at? Is that one in Miami or what? Because I know that you can get that at the Field Museum in Chicago. They got something like that at the Field Museum in Chicago. And there's another one called the Museum of Science and Natural History, also in Chicago. The Field Museum is named after one of the two richest families in Illinois, the Field family. And you were a kid in Michigan, you probably, if you were a kid, you probably went and took a visit to Chicago because that's where you would have seen it. You would have, and I told you the Field Museum. No, the Field Museum has the dinosaurs. The other one is called the Field Museum. It was the Museum of Natural History. If you're in Michigan, North Indiana, you took it to Chicago because that's where it is. Yeah, and I could actually visualize that room right in my head because I've been there because I'm a geek, right? And I enjoy spending time there. And it's all on the lake. It's really nice. I miss Chicago. Oh well, here we go. So let's go ahead and write down the coordinates of this point just in the time that we have left, which isn't a lot. This is x is 300, y is 80, and we have the equation is positive x direct, positive y, it opens the positive y direction, So it's 4ay equals x squared. I'm going to set this at the origin. And so now the equation is going to be, I know that 380 is a solution. So I know that 300 squared, 900 hundred, 900 hundred, 900 hundred is 4a times y is 320 times a. And so a is going to be 32 over 90,000 over 9,000. And 9,000 has 3 2's in it, 8. And so that's 4 over 9 times 125. That's 2 1/4. 9 times 125. That's 1,000, 1125. Somebody tell me if my math is wrong on that. But other than that, I'm going to go for it. Okay, so we've got our equation, right? And so now I know x, if x is 150 feet, I have a times 4 times y. And so the height, y, I'm running through this because we're out of time, is going to be 1125 over 16 times 150 squared feet. And I'll leave the calculation to students as an exercise. Okay, there we are. So when we come back on Wednesday, we're going to turn to the other two conic sections, and they don't work with Directrix forms. They work with what's called a fundamental box. And Pythagorean theorem will play a role. And we will talk about that then. Thank you guys for your attention. Always good to be with you. I wish I could see you too. But I want everybody to stay safe and have a good day, okay? Remember, I'm leaving you until tomorrow night to turn in the assignment, those 5 matrices, and yeah, and a whole bunch of copying. Yes, I want you to copy that nasty thing. You think that's bad? Yeah, oh, let me stop my recording.